The article for today is the cap FAQ. No subject appears to be more controversial to distributed systems engineers than the often quoted, often misunderstood cap theorem. The purpose of this FAQ is to explain what is known about cap so as to help those new to the theorem get up to speed quickly and to settle some common misconceptions and point of disagreement. So I'll cover the key facts that are detailed out in this talk. And you can read the whole doc. It's really good. So here's the first one. Where did the cap theorem came from? Dr. Eric Brewer gave a keynote speech at the Principles of Distributed Computing conference in 2000 called Towards Robust Distributed Systems. In it, he posted his cap theorem, at the time unproven, which illustrated the tensions between being correct and being always available in distributed systems. 2 years later, Seth Gilbert and Professor Nancy Lynch, researchers in distributed systems at MIT, formalized and proved the conjecture in their paper Brewer's Conjecture and the Feasibility of Consistent, Available, and Partition-Tolerant Web Services. Fact number 2. What does the cap theorem actually say? The cap theorem, as for cap, says that it is impossible to build an implementation of read-write storage in an asynchronous network that satisfies all of the following 3 properties. Availability. Will a request made to the data store always eventually complete? Consistency. Will all executions of reads and writes seen by all nodes be atomic or linearizably consistent? Third, partition tolerance. The network is allowed to drop any messages. More informally, the cap theorem tells us that we can't build a database or storage that both responds to every request and returns the results that you would expect every time. It's an impossibility result. It tells us that something we might want to do is actually provably out of reach. It's important now because it is directly applicable to the many, many distributed systems which have been and are being built in the last few years. But it is not a death knell. It does not mean that we cannot build useful systems while working within these constraints. Fact number 3. What is read-write storage? CAP specifically concerns itself with a theoretical construct called a register. A register is a data structure with 2 operations. Setx sets the value of register to x. Get returns the last value set in the register. A key value store can be modeled as a collection of registers. Even though registers appear very simple, they capture the essence of what many distributed systems want to do, write data and read it back. What does asynchronous mean? An asynchronous network is one in which there is no bound on how long messages may take to be delivered by the network or processed by a machine. The important consequence of this property is that there is no way to distinguish between a machine that has failed and one whose messages are getting delayed. Fact number 6. What does available mean? A data store is available if and only if all get and set requests eventually return a response that's part of their specification. This does not permit error responses since the system could be trivially available by always returning an error. There is no requirement for a fixed time bound on the response, so the system can take as long as it likes to process a request, but the system must eventually respond. Notice how this is both a strong and a weak requirement. It's strong because 100% of the request must return a response. There's no degree of availability here, but weak because the response can take an unbounded but finite amount of time. Fact number 7. What does partition mean? A partition is when the network fails to deliver some messages to one or more nodes by losing them, that is, not by delaying them. Eventually, delivery is not a partition. The term is sometimes used to refer to a period during which no messages are delivered between 2 sets of nodes. This is a more restrictive failure mode. We call these kind of partitions total partitions. The proof of cap relied on a total partition. In practice, they are arguably the most likely since all messages may flow through one component. If that fails, then message loss is usually total between 2 nodes. Now, fact number 8. Why is cap true? The basic idea is that if a client writes to one side of a partition, any reads that go to the other side of the partition can't possibly know about the most recent write. Now you're faced with a choice. Do you respond to the reads with the potentially stale information, Or do you wait, potentially forever, to hear from the other side of the partition and compromise availability? This is a proof by construction. We demonstrate a single situation where a system can't be consistent and available. One reason that CAP gets some press is that this constructed scenario is not completely unrealistic. It is not uncommon for a total partition to occur if networking equipment should fail. That's all for this article. Thank you.